Please welcome to the stage today's moderator, the first director of the U.S. National Quantum Initiative, current Microsoft Quantum partner, and a visiting research professor at the University of Maryland, College Park, Charles Tahan, and his esteemed panel. Principal Research Scientist with IBM Research, Antonio Córcoles. Director of the Jülich Supercomputing Center, Kristel Michielsen. Principal Quantum Architect with Microsoft Research, Hongbin Liu. And Vice President of Quantum Systems for IonQ Inc., Muller.
Well, who wants to learn about quantum computing today? Well, I'm honored actually to be here to help open the SC25 with the new kid on the block, quantum computing. We have a pretty cool panel today. I'm going to let everybody introduce themselves just in a minute, with a minute each. You know, why people should listen to you about quantum computing, you know, what your company does or organization does in quantum. Just real quick, why don't we start with you, Antonio?
Yes, well, thank you for having me here. This is very exciting, not only for being the panel, but also seeing that this plenary panel is about quantum computing. So my name is Antonio, I work for IBM. IBM has been in the technology of quantum computing. People might not know that, but for several decades, as Charlie Bennett was an IBMer that was actually one of the fathers of quantum information science. But in practical terms, we have been working with superconducting qubit systems for about 2 decades now. And we really believe in this technology, and we think that it's going to be a revolution in computing.
Kristel.
Yeah. Also, thank you for having me here. It's very exciting to talk about quantum computing in the HPC environment. So I'm the director of the Jülich Supercomputing Center and also the head of the quantum computing activities at the Supercomputing Center. Now, personally, I have been working in quantum computing for about 30 years in the meantime. So it's quite some journey, and the last few years, I must say, it became very exciting, especially coupling HPC and quantum computing.
Thank you, Kristel. Hongbin.
Thanks, Charlie, and thank you for the organizer for the invitation. My name is Hongbin. I'm a principal architect in Microsoft. I started my career as a quantum chemist. I used to write a lot of HPC code and run simulations on HPC clusters until a point I realized there are certain problems like quantum chemistry is out of reach for classical computing, and I started to devote into quantum computing to look for a solution. And as for my organization, Microsoft cares about quantum computing because that's the next frontier of the computational power, and that's the next accelerator for cloud innovation. And ultimately, we see this as the approach of solving many of the most challenging problems of computation nowadays.
Thanks, Hongbin. And Rick.
Hi, I'm Rick Muller. I'm currently the VP of Quantum Systems at IonQ Quantum. Before that, I was the director of IARPA. IARPA has done some of the seminal funding in quantum information science and quantum computing. And before that, I was at Sandia National Labs, where I worked on quantum computing and ran the quantum computing program there. IonQ's founding mission was to build the best quantum computers to solve the world's hardest problems. So this is something written into our DNA there. And we've got a really exciting platform for this, to look at these. Like my colleague to the right, I also came to quantum computing from quantum chemistry. It's a great place to look at this, and I think it'll be one of the real lasting applications of what we're doing in quantum computing right now.
Thanks, Rick. So we have a great panel of expertise here. As Kristel mentioned, many of us have been working in this field for over 2 decades, if not more. My journey started as a grad student working on silicon quantum computing. Then after my postdoc, I went to DARPA, where I helped them start the first big quantum computing programs back in 2005. I then went to the National Security Agency for about 15 years, helping run quantum computing programs, doing research. And the last 4 years I spent doing policy at the Office of Science and Technology Policy at the White House, running the National Quantum Initiative. So, you know, we're already 25 years into this. You know, if you read the news, you might think that this is an overnight success, but there's been a lot of investment in time already getting to where we are. I think the first thing we want to talk about is where we are, but where we think the future is going. So I'm going to ask Rick, you know, give us a brief summary of the field, you know, where we are in terms of the North Star of quantum computing, where we need to get to in terms of application, quantum computing size, and, you know, how long you think that could take to get us, given, you know, your history.
Yeah, so quantum computing uses additional power that's in quantum systems that aren't in classical systems to give an exponential speed up on certain problems that are really, really important. Again, quantum chemistry is one of them, but there are a number of other applications that quantum can do. One of the challenges to date has been quantum systems have more computational power, but they also have more opportunities to make errors. When we built the ENIAC computer, that was already correct. The gates in that, the operations in that computer were already correct to something like 1 part in 10 to the 16 operation. So it was already very, very correct. And I think they worked on some of the early theory of error correction, but didn't need it because it was already accurate enough. You know, today's transistors are correct to something like 1 part in 10 to the 28th or something insanely high. Quantum computers traditionally have made far more errors. And it's been a challenge both to get the error rate of those pure qubits low enough, and then to design error correction protocols that have low enough overhead that you can afford to do something useful with the resulting computer. And what's exciting today is I think both of those things are now coming together. We've got a new generation of quantum error correction codes that have much lower overhead than the previous codes had. And we're seeing real improvements in the fidelity of these systems. My company just joined forces with Oxford Ionics, who recently announced that all of their quantum operations were below 1 part in 10 to the 4, or, you know, they had 99.99% fidelity for all the operations for their quantum computer, which we think is really low enough to do something exciting in quantum computing, and again brings the year where we start seeing quantum impact from something that was nebulous and 10 years in the future to something that we think can happen in the next 3 or 4 years.
So I'm the moderator. I have to love all the qubits, but there are, you know, a good set of competing technologies today: silicon-based quantum dot quantum computing, superconducting qubits, atomic molecular type qubits like neutral atoms, ion qubits, photonic qubits. So maybe a question for the panel: what's the best qubit?
I think I already voted.
Kristel, maybe start.
Yes, so I don't think that a lot has changed in the past year. So we all know superconducting qubits are quite good. They are fast, but they are making, I would say, still quite some errors. Of course, we are now correcting for these errors. And then we have the ions on the other side, they are quite accurate, but in comparison, they are rather slow. So it depends a little bit on what you want to have for your quantum computer. And in our opinion, then for a supercomputing center, we say if this has not yet been decided what the best one is, then we take of each kind one of them, and we in our users will test then which will be the best one.
Hongbin, how many qubits do we need to do something for chemistry?
So I think nowadays we all talk about logical qubits. That's like the version of qubits that is less error-prone, that has high fidelity, can allow us to do something meaningful. And I think on the order of 100 is what we need at least to advance science forward.
100 logical qubits.
100 logical
which
qubits.
turns into how many physical qubits?
I think this is a little bit tricky question. The answer could change.
It's a smart crowd. You can.
Yeah. So
educate them.
this is related to what Rick said, the error correcting code. So basically, you need many physical qubits to make a single logical qubit, and depending on the advancement of error correcting techniques, nowadays, let's say we can say we need 100,000 physical qubits to do that. Or maybe there is something happening in the error correcting that we can use way less physical qubits to make a logical qubits. Then I think the number of physical qubits suddenly will shrink down. And
Antonio, maybe from IBM's point of view, can you tell the logical qubit story and how the field has been progressing?
Yeah, so we obviously go with, we are working with superconducting qubits, and for us, it falls at a really sweet spot of quality, scale, and speed. And we all, as a company, have some level of choice of choosing our platform where we are developing the systems, and that has been the reason for us. Going into your question, the way I try to tackle that question of logical qubits, physical qubits, and so on, is to take a step back and look at what can you do computationally. And I think this will come up throughout the panel, but the computational element for quantum computing is the quantum circuit. So the question I will ask is how large a quantum circuit can you run? And if I will say the width or the number of qubits is 100, that's a perfectly good answer for us as well, because it starts to be in the scale at which classical systems struggle to capture. And then in terms of like what kind of error level you have the depth of the circuit, or how many gates you do. When you understand the capabilities of your machine in terms of what kind of quantum circuit you can run, then the question of how many physical qubits is abstracted. And I put that on the responsibility of the vendor, because as Hongbin was saying, the choice of code has a very important impact on that number.
But in the interest, we should probably mention for the audience that there are other qubits present, right? So there are neutral atom qubits, and neutral atoms are another. IonQ works on ions. Neutral atoms are the other big atomic system, and the big breakthrough that's happened over the last 5 years there is to go from kind of shallow kind of egg carton-like potentials. To these optical tweezer arrays that have really energized that field. I'm surprised no one has mentioned topological quantum computing, given that we have.
Thanks for bringing that up.
Microsoft, and I'd love to hear from either one of you on where Microsoft thinks that technology is. There are photonic quantum computing approaches. The company PsiQuantum and Xanadu are both making a lot of excitement in that area. Have we left anything out?
Electrons on liquid helium?
Electrons on our helium, yeah.
There are many types of qubits. I mean, when I started in the field, this is 20, 25 years ago, we literally had no idea what the qubit modality would be. We're trying to make the equivalent of a transistor, but quantum. An object physically realized that can be 0 or 1 or a superposition of those states. And there are many physical systems that could realize them. The spin of an electron, the two levels of an atom, artificial atoms like superconducting qubits, more exotic topological particles which have some nice properties in terms of immunity to noise.
Polarization of photons.
Polarization of photons. So there's many different realizations. We need, as a field, to find the qubit that will work first. So it lasts a long time, it behaves quantumly, you can do operations on it. And that's really what the last 20 years were about. Now we have a number of contenders. I would say, and I'd love to hear the panel's feedback, like the next 5, 10, or more years will be about how do you turn those into systems of potentially hundreds of thousands of quantum transistors that will work together in this probabilistic machine, but at the end give you some chance of success. Like that's really the challenge we face as a community. Love to hear anybody's opinion on other big challenges.
You're thinking about kind of a scale.
Yeah, what's preventing us from scaling up? We have systems now, hundreds, maybe 1,000 different types of qubits. We think we need to get to 10,000, 100,000 potentially, million potentially. What is holding us back? And what do you think would be, if solved, would be the biggest accelerator of that progress?
So there are progress that needs to happen at different levels. The system itself, I'm going to focus on superconducting qubits because that's what we have more or less clear in our team. We do need to improve the noise of these systems at the physical level. And we have made quite a bit of progress over the last couple of years. We went down kind of an order of magnitude. And as Rick was saying, the noise of these systems is really, really high compared to the technologies that people in this audience will be familiar with. But we don't need to reduce the physical noise to arbitrarily low levels because we have error correction techniques, but there are other techniques also that will help us extract some useful computations before error correction. We call error mitigation techniques as well. And at the level where we are now, getting another order of magnitude, which is not out of reason in the next few years, will allow us to start tackling circuits that are of the order of 100 qubits and a few thousand gates. That's already starting to be something that can be of use. But going further with error correction, right, the level of noise that we need to get to at the physical level, we are not there yet, but let's say we are at a factor of 100 or so. We cannot keep arbitrarily reducing that noise. So quantum error correcting codes will take over. And one of the main challenges, and Rick was surfacing it, is how to come up with codes that are efficient, codes that don't take many physical qubits per logical qubits, but at the same time, codes that can correct a reasonable amount of errors. So in recent years, there have been a lot of progress in that area, theoretically. Our team is pioneering some of the what we call quantum LDPC codes, and getting to realize those physically is a big challenge. Different platforms will have different challenges. In our platform, the topology of our system, which is solid state, is quite demanding. So at the fabrication level, we had to solve a lot of challenges. We had demonstrated a few of those, and we have our roadmap, right? The scale at which we will be getting in the next, let's say, 5 years, with error correction will be quite substantial. Still, like this million of qubits that Charlie was saying, I think, and I'm referring to circuit size, or logical qubits, if you will, I think it's a bit further. But we are thinking a couple of thousand qubits, a billion gates is something that we have in before the next decades, let's say, by the early 2030s. That's at the system level, but one thing that quantum computing also needs to come forward is, and I'm sure we are going to dive deeper later, is quantum algorithms. Because there is not a large amount of quantum algorithms, and we're going to talk about applications. there's an underlying level, which is the algorithms that enable those applications. And to me, or my experience has been, and probably the HPC community has seen that, you come up with algorithms when you have your hands on cutting-edge systems. And having systems that are of reasonable size, let's say 100 qubits or so, and experimenting with them is very important. Right? So that's something that we want to keep enabling and trying to figure out ways of making that availability broader. And going back to our correction, the finding the codes is not enough. You need to build, engineer an architecture that supports those codes. And that's where also there is a very natural interplay into potentially HPC and quantum, right? And how to take those syndromes that signal where the errors are and process them in a time that is commensurate with the operations of the qubits, which is quite fast. That's a challenge that is really starting now as we are putting the first systems together. It's very exciting. And that's, I think, the next big breakthroughs that I anticipate in the next few years.
So just to summarize for the audience, if you're new to the field, we've been talking about 5 or 6 or 7 completely different types of technology, totally different ways to make quantum transistors. They've been developed over the last 2-3 decades. We now have systems, with tens, hundreds of qubits. We think we need to get to very large systems because these things are delicate. They decay very quickly, which means their error rates are very high. So you need to have error correction, a lot of error correction. And because the whole machine is probabilistic, the error rates have to be pretty low for you to have any chance of success. That's where we are as a field. So quantum computers are not easy to build. We still have ways to go. That's only the first part of the problem. And as Antonio was trying to say is, we now have to figure out what you do with the quantum computer. So from the point of view of this, Rick, what would you do with a quantum computer in the next 2 years? What is going to actually provide value to customers?
I was going to take a step back and actually try to put it in terms of HPC, since we're at an HPC workshop, right? So what do you want in an HPC computer? Well, you want every computational cell to reproducibly give you the right answer, and then you want a whole lot of those computational cells, and then you want some way of then addressing and controlling that conglomeration of things. And Antonio kind of covered those in his answer there, right? So you want each one of the computational cells to give you the right answer, and in quantum that means you need to kind of make logical qubits as an encoding of a lot of the bare physical qubits. But then you need all of those to be the same so you can then kind of address those and get collective computation out of those. And then you need to be able to kind of control that entire system as a whole. So we know how to do some things. Richard Feynman started a lot of this off by noting that when you try to simulate quantum systems using a classical computing system, there's this exponential overhead associated with representing quantum states. There's this tensor product that you have. And Feynman noted that there's no reason to think that physical systems have to do an exponential amount of work to find their own ground states or something, so that maybe quantum systems intuitively know how to solve quantum problems, and if you could build computers out of those quantum systems, you could solve those problems. Many of the solutions we have today look like physical simulation systems. Again, that's why people came from quantum chemistry very often, or quantum physics, because those things naturally lend themselves to efficient solutions on quantum computers. So there are solutions like quantum phase estimation that look a whole lot like solving eigenvalue problems on a classical computer. And so those are some of the examples of algorithms that are unique to quantum computation, but that do similar things to things that you might run on an HPC system.
So thank you, Rick. Let's talk about this notion of combining HPC and quantum, because it sounds nice. What does it actually mean? Maybe I'll start with you, Kristel. I assume your center has thought about this a lot. What does it mean in real life to combine a quantum computer with an HPC supercomputer?
Yes, so I first want to put some things maybe in a perspective. If we want to simulate a universal quantum computer on a classical machine, we recently have set a new world record, so we can now simulate 50 qubits of a universal quantum computer. But for this, we need Jupyter, which is the first exascale machine in Europe. So, and then we are only talking about 50 qubits. So the colleagues here have been talking about experimental systems, real quantum computers, now between 50 and 100 qubits. And then you can imagine you can do much more with this. And then I'm not yet talking about the resources, because the resources required to run an exascale machine is, of course, much more than a quantum computer. Now, why combining quantum computers and HPC systems? First of all, we are very often talking about universal quantum computer, but a quantum computer itself is not efficient to do any any specific calculation. We can think about adding numbers. Now, for this, you are never going to use a quantum computer because it's not efficient. Of course, our classical computer can do this very efficiently. So we have to look for problems that the quantum computer itself can solve much more efficiently than a classical computer. And then we come back to these quantum systems that we are, I cannot say not able to simulate on classical systems, but it's a huge effort. So if we can give these parts to the quantum computer and do the things which are very efficient on a classical computer and put the best of these two worlds together, so tightly integrate the quantum computer with your HPC infrastructure, then we can use the quantum computer as a kind of accelerator, a new type of accelerator for the computation. Does this mean it always accelerates? Maybe not, but it might have another advantage. And the other advantage is definitely that it will use much less power than your classical machine. So in the HPC community, we have to look in our workflows and look for these particular pieces in the software code that we can give to the quantum computer. The quantum computer calculates it, gives the solution back to the HPC system, and in an iterative loop solves the whole problem, the hybrid system.
Well, let me push on that a little bit. Like, how mechanically does that work? Like the combination of quantum and HPC, like how hard is it? Like, what are the things that does this community need to solve to make that happen? Maybe I'll start with you, Antonio.
Yeah, so as Kristel was saying, I think there is a separation that happens at the problem level of identifying what are the pieces that are hard for a given technology and what are the pieces that are easier for a given technology, and then diverting the problem to those. In terms of system architecture, different use cases might call for different levels of connectivity. There are some algorithms that might require the quantum to work a little bit separate. Other algorithms might call for more interconnectivity. But that's kind of like some of the other set of tools that we need to work on expanding at the workflow level, workflow management level, and so on. But this kind of connectivity, it has to take into account that, and it was mentioned already, there is a very different bandwidth and speed at which these machines work, quantum systems work, and that poses a clear kind of bound on what is the need for transferring information in the input and the output. And the inputs can become quite substantial, and trying to target in efficient ways to pass that workload to the quantum computer as they scale is going to be a challenging problem. That's another area in which HPC also potentially can help at that level. But there is a variety of scenarios in which I think we are going to see this interchange of information working in different ways between the two systems, and how much connectivity, bandwidth, and so on we need. It will evolve with the use cases that we find. Then there is another layer underneath, which is, as we were saying, related to error correction, and there the bandwidths become a lot more tight because there is what we call real-time and operations that you have to do within the lifetime of a quantum circuit, and that is both a lot of speed that you need in moving data and processing data, and the size of the data can be substantial as well. So there is architectural problems that we need to tackle when it goes all the way to defining the error correcting code, potentially having concatenated code so you release a little bit of that latency demand. But that's one aspect in which I anticipate there will be a tighter connectivity, whereas at the application level, the connectivity, it might still need to be somewhat tight, but it can probably be relaxed a little bit.
But if you think about how people currently do GPU programming, right, you need to take care on where your data is and when you move it onto the GPU and what part of the computation you're doing on the GPU and how you move that back to the CPU. And these are all in a system like CUDA that has software tools to do all these things that at the end of the day you link into a large application. I think when quantum systems are mature, it's not ridiculous to think that they'll have the same types of tools and the same types of considerations to make them work. In other words, you will have parts of your computation that you're going to run on a quantum processor and parts you're going to run on a classical processor. And just like CUDA processing, you're going to need to think carefully, this is where the bandwidth comes in, how you're going to move all that information onto the quantum processor, how you're going to get it off. There's some really nice work that Matthias Treuer did looking at what problems are going to work well on quantum computers. And Matthias looked specifically at the communication bandwidths you have getting information on and off. At the risk of seeing every problem like a nail or every problem like a quantum chemistry nail, one of the advantages to chemistry problems is there's normally a small amount of information at the beginning, and there's a small amount of information at the end, and there's a huge amount of computation in the middle. And that's ideal for the types of things that are going to work well on quantum processors, because you can get that information onto the processor efficiently using, order n type work. You're going to do some huge amount of work that is polynomial time on the quantum processor, but would be exponential time if you were doing it exactly classically. And then you're going to move a small amount of, order one type work back off the processor again. And it could end up looking very much like what we're doing today with GPUs and CUDA programming.
Yeah, before we leave the HPC topic, let's spend a moment to talk about how incorporating quantum computers into data centers for HPC will look different. Maybe, Kristel, you can say, what are you doing to prepare European data centers or HPC clusters for, the future of different qubit modalities?
That depends very much on the type of technology that you have. So one thing is most of the quantum computers you can simply not put next to your classical HPC system. They are rather sensitive, so temperature sensitive, but also sensitive to vibrations. As I mentioned, not all of them are as sensitive, but if you have a vibration-free floor and things like that, it usually helps the quantum computer in its efficiency. The other thing is you want to connect them tightly, and the question was, how do you do this practically? Even if the quantum computer is in a building near to your data center, that's in principle for now sufficient for the latency. Although you want to have them, of course, closer to each other, but I would say for this stage it's fine. And then it's a matter of software. And we see this now. So a lot of hardware, different hardware types have been produced in quantum computing and tested. And now we are in the stage that we need to develop this full software stack. Because if we want to have users using these hybrid systems, it has to be simple and user-friendly. And this will depend very much on the software stack. And also for this, you have to prepare. Because we as a computer center, we do not want to have this different for every different type of quantum computer. We want to have it agnostic.
I mean, does software ever even matter anymore? I mean, we have AI. Doesn't that solve everything? I mean, this is a serious question. Is it?
I think the software matters a lot. I think one thing that I like to think about in terms of quantum computing is the programming model is the quantum circuit. And that comes with some weight on it because you have to run approaches to prepare it for execution that have to be respectful of that programming model. You cannot, or you can, but you pay a price. Slice a quantum circuit in many places and optimize in many places, because when you put it all together again, you pay an exponential price. So that part, and I agree that you need to build software that is agnostic to the platform at the closer to the user layer, and then there has to be another level of processing that is responsible, the system is responsible for, to take that kind of prepare a circuit and optimize it for execution and the specific physical system. But I think capturing the needs for optimizing quantum circuits in an environment where you have also the need to optimize other kind of computational elements like tensor networks and so on, that is very important.
I want to talk about AI more and software, but before that, there was a statement made by Kristel about quantum computers requiring much less energy. Is that true? And why is that true? I want to push back on that. Maybe Rick, what's your opinion on that statement?
So the statement I need to defend is that quantum computers use less energy.
Yes.
Okay.
Kristel made that statement.
Okay. So here's the argument for that. And the reason Charlie's having a hard time believing this is that to do the types of isolation that Kristel mentioned and that you need to make a quantum computer work, you typically need a lot of environmental control. So superconducting qubits work in dilution refrigerators. IonQ builds HVAC systems into their data center computers just to be able to control that. Yet with all that environmental control, you can still argue that quantum computers that if you were to solve the problem classically, it would require vastly more energy than the quantum computer requires, since there is that exponential speed up that the quantum algorithms give you. So that if you really want the answer to a hard problem, you'll actually use less energy on a quantum computer just by virtue of that exponential speed up you get.
Yeah, so quantum computers are really bad computers. They're slow, they're hard to build, they take a lot of energy to run, but for certain problems, they're exponentially better, and that's where the energy savings can come from.
Yeah,
That's the summary. Okay, back to AI. So if you read the newspapers, which I don't recommend with respect to quantum, AI and quantum are going to change the world. I mean, AI is certainly changing the world. How practically do you see quantum and AI converging for algorithms? Maybe I'll start with Hongbin.
Yeah, so I think nowadays you see many combinations of quantum plus AI. They can be interpreted in different ways. Of course, you can say AI nowadays, especially with the great advancement of language models, they can understand the quantum programming language, they can optimize your circuit, like they can help on quantum computer. But I think the real value of this combination comes from the way that how quantum helps AI. Ties back to the statement we have that quantum computer is a bad computer, but it is good for something. And this something in terms of application is what we believe things like quantum chemistry, condensed matter physics. It solves very specific problem like Schrödinger equation in a very exact way once you have the quantum computer at such scale. And this is because for problem like Schrödinger equation have very specific structures. They are all what we call exponential scaling speed up quantum algorithm that allow you to do way less operations on a quantum computer to solve it exactly, comparing to its classical rivalry. So now think about you have a computer can solve those problems exactly. What can they do? What they did is they actually pushing the limit of computing to the regime where classical HPC cannot. They can solve those Schrödinger equations, chemical system, electronic structures exactly where the classical computing cannot. Think about nowadays when we talk about application in chemistry and material science domain, we talk about training machine learning models with data of those approximated methods running on the classical HPC. That's actually 50% of the classical HPC workload in most of the supercomputing centers is running those DFT, molecular dynamics type of calculation on chemistry and material system. We use those approximate data, we already get a pretty good, say, machine learning model, AI model, machine learning potential that can solve a lot of material problems, understanding material and chemistry way more efficient than we used to be. Now, if we have a machine that can give you exact data, even though those data are not going to be a huge data set, those are not going to be 100 million data points, those might be 1,000 data points from a quantum computer. They can be used to fine-tune those foundational machine learning model for chemistry, for material, allow you to exploit those systems much more accurately. You can think of this quantum computer once it operates in scale, solving those quantum chemistry problem, quantum condensed matter physics problem. It is going to teach AI quantum physics. I think this is the greatest disruptive value comes from with this combination, quantum plus AI.
But there is another application which came out of John Preskel's work at Caltech and his co-workers who showed that if you've got a quantum state somewhere, you can learn that quantum state using quantum operations exponentially faster than you can using classical operations, that is measuring everything and trying to fit a statistical model to that. So, I think it's natural to ask yourself, I don't have a lot of quantum states sitting around that I want to learn. Why would I ever need to do anything like that? And the point is that there are a lot of other ways of acquiring quantum data. So there's this whole other class of methods that we will probably not get to called quantum sensing. And you can use the same types of quantum effects that we're all talking about to make faster computers to make much more sensitive sensors. There might be a situation where you've now started to run some quantum sensing operation to determine whether an asteroid is going to hit Earth or not. And that data might live on 1 million different satellites that are all in, geosynchronous orbit or maybe MEO or something. And they're distributed over all of those systems. You might be able to kind of get the answer, is the asteroid going to hit Earth? You might need to query all of those sensors. And what Preskel's work shows is that it's exponentially faster to learn that answer doing quantum operations than to do classical operations. And that's one of the more exciting applications that combine machine learning and quantum computation that I see out there right now.
Any other applications worth talking about?
One thing I will say about that, which in my mind has never been very clear, is that you still need to load the data into the quantum computer, and that takes gates.
Right.
And it's easy to lose the speed up if you are not efficient in that.
Yeah. Yes.
Unless the quantum computer is the sensor. Before we leave that topic of AI and quantum, any other contrasting opinions or interests?
I would say nowadays also AI is already used for the calibration of quantum computing. So that's then more on the technical side, on the construction side of the quantum computer. But by itself, that's of course also a kind of application. So it's not running AI on the quantum computer. So there you have to look into quantum machine learning and see how it goes from there. So also image recognition could be one of the examples.
So Rick mentioned sensing. You might have also heard about quantum networking, which is a whole entire field itself. How does quantum networking relate to building quantum computers or not? Maybe I'll start with Antonio.
We were talking about sensing? Or?
Yeah, connecting quantum computers together.
Yeah.
Is that worth doing? What's different about it? What does the audience need to know from an HPC perspective?
Yeah, at the technological level, there are different ways you can envision that. You can connect, let's say you can do long-range entanglement across modules, and that, there is some technology today, at least for superconducting qubits, that we can exploit in that. And then there is another level that can potentially be more powerful, which is through, in our case, again, for superconducting qubits, to a physical process called transduction, which takes the photons that our processors understand, which are at the microwave region, and take it to optical frequencies so you can take the information outside of the cryogenic environment to another cryogenic environment. That kind of networking in the quantum sense is still in the very early days of research. I think it will come at some point, but I see a lot shorter term applications of distributed entanglement within a cryogenic environment and scaling in a modular way our quantum computers through processors that can have a specific number of qubits, or it can have a specific size of error-corrected memory that you can connect together.
But one of the advantages that atomic systems have over superconducting systems is a much easier coupling to photons. And so one of the things we're seeing in ionic systems is that some of the traditional bandwidth issues. So people have had the theory of coupling ions together using photons for 25 years or so ago. I think Chris Monroe who was the IonQ founder, did some of the seminal work in that when he was at University of Michigan, I think. But to date, it's been slow, because what you need to have happen is you need an ion to emit a photon and another ion to emit a photon, and both of those things happen at the same time, and do some heralding calculation that shows that everything's great, and then you've entangled those two ions. Some of our colleagues at a company called LightSync developed a quantum memory technique that uses these diamond. That was one of the technologies we forgot to mention in the beginning. You can also use diamond defects as a source of our qubits. But diamond defects often are used more as either magnetic field sensors or as quantum memories. And you can make a quantum memory that's long enough lived that you can speed up that exchange of photons. So instead of having that n squared effect of two low probability events happening at the same time, you can collect one, wait a second, collect the other, and then herald that. And that dramatically improves the bandwidth that you can do networking with. And once you can do that, you can do a lot of cool things like distributed quantum computation. I mean, you know, the way we build computers is we have a bunch of modules and we connect them through some kind of network. And you might do some of the computations on one system and transmit data to another system. You can do the same thing if your quantum network's good enough. You can do distributed quantum computation where a bunch of separate quantum computers look like a single quantum computer. And that's a really exciting application. You can also do cool stuff on top of that, like blind quantum computing, where you can send data to a quantum computer, and that computer doesn't even know what it's operating on, so that it kind of has the same advantage that homomorphic encryption might have on a classical system. So you can then distribute a system across multiple processors, and none of those processors know what computation is being done across them. And again, quantum networking opens a lot of those doors.
Yeah, but I think from a computing perspective, the need of the networking is also tied back to the qubit modality problem, right? So depending on what modality, what qubit techniques you are building off, and how it scales. When I say when it scales is when you go to, let's say, 1,000, 10,000, 100,000 of qubits, how large is the quantum computer? And if your qubit technology allow you to scale it in a very efficient way. For example, I now bring topological qubits. So you can scale to 1 million qubits still within a size of like a chip, like on your palm. Then in this case, you probably don't need a networking to connect two quantum computers together because a single chip allows you to do meaningful computation already. And but for some other modalities, like if you scale up to such a size, 110,000 or even 100,000 physical qubits, the machine itself is too big to fit on a single wafer. Then that's the time you need to think about how do I need to connect. I have to connect that because I need to have the connection between two machines to do meaningful calculations. I think the necessity of the networking also goes back to the modality problem.
But I also would like to do a different thing. Instead of connecting the quantum computers, I would like to connect different quantum computers to one HPC system as different modules, and then use different technologies so they have all their own characteristics. And then in my workflow, I have a choice of the properties of the different machines. So, and then I can couple an analog quantum computer, a digital one, so with circuits, gate-based, and the other one, an analog type. Plenty of possibilities.
Well, thank you. I think those are great comments. Let's change gears really quick towards the end and talk a little bit about policy and funding and the state of the field. You know, I mentioned that we've been doing, some of us have been doing this a while, and in the first 10, 20 years, most of the funding came from government agencies doing, supporting research. And now you've seen in full force industry coming into this in the last 5 to 10 years. You know, how do you guys see, what are the needs of governments, countries, nonprofits? You know, why do they still need to be involved here for workforce, for research? Maybe start with you, Kristel, or Antonio.
Yes, for us, that's essential. So our quantum computers, we have now 5 different ones. They are all funded or by the European Commission. So European level, on a national level, and also on state level. Sometimes a combination of these three even. So for us, that's really essential that there is public funding in different type of projects.
What about for companies?
Well, but there are two different ways that the government typically develops a field like this. Initially, government wants to reduce the risk so that companies are willing to invest in that technology at all. So in the very early days of IARPA, a program manager then named Michael Mandelberg started a program called Multi-Qubit Coherent Operation. And this was in the days when a lot of people had a working qubit in some physics lab somewhere, but it wasn't at all clear that people could put a whole circuit together and get the right answer out of it. And MQCO, showed that that was the case, and a lot of the people that now have programs, so Google's program came out of John Martinez's program that was an MQCO performer. IonQ came out of Chris Monroe and Jungsang Kim's work that was funded by MQCO. IBM was funded by MQCO. So that was a really important investment just to show that there's something there, that this isn't just smoke and mirrors, that you can run a circuit and get the statistical distribution that you expect to get out of it. But fast forward another 15 years, and now, the companies here are spending vastly more than an organization like IARPA can put into a program like that. And that's a little depressing if you're the director of IARPA and you want to create the next amazing program. At the same time, it's a real sign of success for that government investment, that the government has reduced the risk enough that companies can now, put vast amounts of money into that research moving it forward. But then the other role that governments play, and this is what Kristel pointed out, was that governments are often the first customer for that new technology. And even if the government can't be the funder of, the kind of funder of last resort in quantum anymore, it's still often the most important customer for those early things.
And what is also essential is, for us at least, so we have the funding from the different governments, but on the other side, what is also essential is the partnership we then have with the vendors, because it's also a research collaboration. We are still in a research phase. We still have to discover a lot. And the best way to do this for us is to do it together with the ones who have built the quantum computers. That's essential.
And HPC went through a similar transition, right?
Yes.
Back in the, I was at Sandia National Labs for 21 years. And back when I joined Sandia and Los Alamos and Oak Ridge were building the fastest supercomputers in the world. And that was awesome. It was just really amazing to see these things come out there. They wrote the operating systems. It was amazing stuff. But of course, industry got to the point where they could do all of those things really, really well. And now when a place like a US National Laboratory wants a computer, it doesn't build it from scratch itself. It works with one of the vendors to then tune, the communication fabric to whatever problems they anticipate solving on that system there. And one would imagine, again, when I joined Sandia was building trapped ion quantum computers. And again, as somebody that was intimately involved in that, I will still be sad to see a day come where Sandia is not building really good trapped ion quantum computers. But you can imagine a similar transition coming where at some point it's the national laboratories or the research institutions aren't going to be building the systems themselves. They're going to be working with vendors to ensure that those solutions can solve the most important problems that institution is going to have.
I would just say that, somebody who spent also 15, almost 20 years in government and is now in a company, we need all the help we can get. So please continue to help us, governments, scientists, other companies.
If I can add a point to what Rick said. I was part of the MQCO and then the logic program that followed it.
Okay.
And what you said really resonated because I think it was somewhere through the logic program where we became, let's say, economically stronger than what IARPA could do. But to me, that doesn't mean that that cycle is over, because there are questions about quantum computing that still belong in a small research environment.
Yes.
And they are going to benefit the technology at a different time scale or at other times.
Yeah.
And one other aspect in which I think the government might play a very critical role as a first customer or a very important customer is, as I was saying about algorithm discovery, putting these systems in the hands of the users and making that available can be done through these programs. Can be, like, the national labs serve the scientific community, and HPC centers that are publicly funded can also fit that role.
So we need to get to Q&A, but just to summarize, we still need to make better computers and we need to find more applications. I think we can all agree on that. So let's end our panel with predictions, which is the best part. And here's the scenario. We're back here, SC28. What will your company or organization announce, and why will you find it surprising? Start with Rick.
So
I'm going to allow you to get into trouble with your bosses. Just,
okay.
You've got my permission.
IonQ will have quantum advantage by 2028. We'll be doing fully error-corrected quantum computation on real problems of importance to industry by 2028. We think, realistically, we have it maybe by 2029, I think, is what's in the official roadmap. But efficiencies happen, and I think if we turn it up to 11, we can get to quantum utility by 2028.
Hongbin.
So I think by 2028, we can have the quantum computer start to train the AI model on quantum physics. We can start to use it to generate exact data of Hamiltonian systems that are not tractable by classical computing. It doesn't mean, it will be a surprise if by that time those data are for realistic chemical system. If we can decipher that will be great. It will be a very sweet surprise, but I doubt that. But still optimistically, I think for many we call model Hamiltonian system, model physics systems, we can start to use quantum computers to solve that and use those quantum generated data to train AI models.
Kristel?
By 2028, we have coupled at least 2 quantum computers to Jupiter, our exascale system. And the users of our quantum computer user facility, which are coming from academia and industry, can use this and will use this to run hybrid quantum HPC simulations for different types of applications.
You mentioned the word surprising. I'm gonna say by 2028, I'm not gonna say anything surprising because we have a roadmap, and I expect we're gonna fulfill it. So we will have fault tolerance, and that is a strong statement because fault tolerance requires a lot of things, similar to what Rick was saying. Error correction in full maturity for running large circuits with high fidelity. If you want a surprising thing, I'll be surprised if RSA 2048 is solved. Right? It's broken by 2028.
Well, I'm the moderator. I have to love all the qubits. But I'll say I'm surprised today that the future looks more like Star Wars than Star Trek, which is hard for me to admit because I became a scientist because of Star Trek. I think by 28, I've told you multiple times, in our last hour that building a quantum computer is hard and has been hard and iterative. I hope by 2028, I think we'll be surprised that we look back and say, wow, that's easier than we thought. And I think the progress of technology is going to accelerate over the next 5 years, more than any of us can really imagine. So with that, we have about 15 minutes for quantum Q&A, which is the best part, because I know there's probably a lot of questions people want to dig into with this panel. So thanks to the panel again, and looking forward to your questions. So I can't see anybody. So
yeah, we can't see you at all.
Whoever wants to come up should go to
I think there are microphones in the aisles.
Go to the light.
There's one over there.
Why don't you just start there?
Okay, I'll start with a thank you for the panel for the nice introduction to the topic. I might be a bit ignorant about the topic, but here's my question regarding error correction. Let's say I have a problem where I can verify the solution. I can just run the algorithm with error correction and let's say 100,000 qubits and get the correct result first try. Or I could run the algorithm with 100 qubits, but with reduced error corrections or no error correction at all, and just try until I get the correct result, and then verify if I have the correct result. So my question here is there a trade-off between error correction and just trying again?
Who wants to take that one?
I think the answer is yes, and there are approaches that are not fully error corrected, but with some sort of mitigation that has a worse overhead than error correction. And it might be preferable at some point to choose that other approach because the runtime might be different, the system complexity might be different, and you might have a benefit in running it many times if you can easily check versus having a more complex circuit and system to do it once. But it depends really on the relative complexity of the problem.
I think some numbers might be useful for you. So physical qubits today have error rates about 10 to the minus 3.
10 to the minus 4. 10 to the minus 4.
Some are better than others today, but we're all improving, which means you can run them 1,000 times before failure, right? The logical qubits we've been talking about are 10 to the minus 12 to 10 to the minus 17. So if you just think about how many operations you could run if you multiply 99.99 times 100 versus 99.999999999, the first one you're going to get garbage most of the time versus the logical qubit machine. And
but
that's really the difference.
I was also trying to put a little bit more complexity in the answer in that is true, but you could have approaches like, let's say you don't error correct, you error detect. And you easily can check, oh, there was an error here, I'm going to throw this away and repeat again, right? It has some nuance.
Let's take the middle speaker.
I think the one speaker on the right was first. You want?
Hey, thank you. James Mannion, Raytheon. Hey, Antonio talked about some of the hardware challenges with quantum computing, and Rick talked about some of the software algorithm challenges, but workforce and talent challenges sometimes can be just as daunting. And sometimes things like AI and ML can kind of distract talent and pull talent away from other key industries. But what are some of the things you all are doing to kind of cultivate and attract and gain new talent in the industry? Thank you for your question.
Well, I'll just start by saying, one of the big motivations for the National Quantum Initiative in the United States was to create more talent, bringing the Department of Energy in full bore to the quantum enterprise, generate a lot of new students and researchers, doubling the funding of quantum research to help do that as well. So that's one thing, but it is an issue. We don't have enough quantum people. It takes, even if you come out with a PhD in something related to quantum physics or EE or something useful to building a quantum computer, it often takes at least 2 years to be able to learn the lingo and work as a part of a team. So it's just something that everybody has to focus on.
Yeah, but I think success is going to depend upon making quantum computing, making people not need a PhD to contribute to quantum computing. And so there, under the NQI funding that Charlie and others helped establish, one of my colleagues at Sandia, Megan Ivory, put together a program. Well, she put together 2 programs, one of which taught quantum computing ideas to high school students over the summer. But then the other one actually put working quantum hardware into New Mexico community colleges. She called it the Quantum Learning Lab. And the idea was, you know, if people understand how to tune up an optical system or run a dilution refrigerator, you know, you don't need PhDs to do that. That is a technology like many other technologies where you just learn how to do it well. And I think one of the things that we really want to see is the benefits of the quantum economy extending beyond those who have PhDs and academic positions somewhere, and have more, you know, people in regular jobs being trained to work on quantum systems, to maintain quantum systems. I think that's completely possible.
I want to add on what Rick said. I think the workforce development is not only is to attract people without PhD degree to the quantum field, but also how we capture a more diverse background of people that coming into the field. As you notice, like there are 2 chemists on the stage is working on this field, and for most of the university in the US, I don't think there is a quantum information science or quantum technology program many years until only a few years ago. And the current working force of the quantum technology comes from the physics, chemistry background, maybe electric engineering. Like it's kind of like a very diverse STEM background. And I think one of the things for workforce development is how to further attract people in this already STEM like workforce to train them into the quantum field.
Okay, let's take the middle.
Yeah, I was curious. I didn't hear much about quantum networks and quantum internet. Do you have any thoughts on that and where it's going, what the current challenges are?
I thought we did talk a little bit about quantum.
I might have missed that part of the talk.
Yeah, no. So I think, you know, Antonio talked a lot about being able to share entanglement among superconducting processors. And then also talked about transduction operations where you can couple the superconducting microwaves to photons. And so you can then network different systems together. You know, and then I think Kristel pointed out that, you know, her dream is to be able to sit in her office in Jülich and have all these amazing quantum computers all networked together, and she pushes a button and runs it on the IonQ system, and she pushes another button and runs it on Microsoft's topological system, and pushes another button and runs it on IBM's system, or maybe runs part of the computation on IBM's and part of it on IonQ system. So I think that's evolving as we're getting better at coupling quantum processors to what in the field are called flying qubits, something that can just move around easily without generating a lot of error.
Let's try to get a couple more right here.
Hi. So as we are making progress here, like as everyone said, like we need to work more on algorithms, software stack, fault tolerance. And all of that research requires access to quantum hardware, which is difficult a thing to get today. And like, what can we do to gain more access to quantum hardware in today's world?
You can log into Azure and...
IonQ systems are on all 3 public clouds.
I think one of the great benefits that quantum computing has over classical computing historically is that we already have the internet. And so many companies now are making their nascent quantum computers available. They're starting to cost money because they're expensive to run. So I think broadening access is something that we can all work together to help to bring new people into the field. But I do think that is something we can do.
Yeah, we do give everybody 10 minutes a month for free, which is not a large amount of time, but we are looking at how to extend that through partnerships and through collaborations. And it is, for us, it's something that we worry about because we really want these systems to be used. But yeah, it's an important challenge.
Yes, so in Europe, the situation is such, like in the Jülich Supercomputing Center, we are running a quantum computer user facility. So their users, as I mentioned, from academia, but also from industry, can have access to these quantum systems. So we provide them with easy and affordable access. And in Europe, there is the European Commission via Euro HPC funding several projects where quantum computers can be acquired and then integrated with various HPC infrastructures in the various countries. So, and in Europe, the goal is then to create out of this one big federated system so that every European, let's say, citizen can choose which hybrid system he or she wants to run the problem on. So this is a very dedicated program to give European researchers from industry access to also different types of quantum computers connected to different types of HPC systems.
So we're out of time. I wanted to just thank our panelists again and the audience for showing up tonight. I think we enjoyed talking about quantum computing. I hope you will learn more and join the field.